tend to think of science as this pure quest for truth, right? But what if some of our biggest discoveries aren't discoveries at all? What if they're just echoes of our own methods? In this explainer, we are digging into a pretty radical paper called A New Map for Science. It's a framework that might just help us tell real knowledge apart from the illusions we sometimes accidentally create for ourselves. So get this. What could possibly connect a giant cosmological mystery like dark matter, a fundamental biological idea like randomness and evolution, and a tricky neuroscientific problem like figuring out what brain scans really mean? You'd think they have nothing in common. But the framework we're exploring today suggests they actually share a deep common root. So here's our game plan. First, we'll tackle the main challenge, how to tell real knowledge apart from a scientific artifact. Then, we're going to dive into the two huge concepts from this new map: invariants, which are the signals of genuine knowledge, and artifacts, which are basically patterns of interference that create all the noise. After that, we'll see how this applies to the whole dark matter problem, and we'll wrap up with a totally new way to think about science itself, as a kind of advanced cartography. Okay, first up, knowledge or just an artifact? This question, it gets right to the heart of what science is all about. How do we know for sure that we're seeing a real signal from the universe and not just noise created by the very tools we're using to look? The paper draws a really clear line in the sand here. On one side, you have invariants. Think of these as the unshakable mountains on a map. They're stable features of reality that are always there no matter how you look at them. This is the good stuff, genuine knowledge. But on the other side, you have artifacts. These are more like the shadows cast by the mountains. They change depending on the time of day, your angle, where you're standing. They describe your process of looking, not the mountain itself. And here's the real danger. If you mistake a shadow for a mountain, you can end up chasing what the paper calls pseudo-problems, illusions created entirely by your own equipment. All right, let's get into the first major insight from this framework. Let's talk about where that genuine knowledge, those invariants, actually come from. Okay, so the paper argues that the source of all true knowledge is something it calls a singularity. Now, I know what you're thinking, black holes, right? For a second, just put that idea aside. In this context, a singularity is like a fundamental anchor point in reality. It's topologically protected, which is a fancy way of saying it's like a knot in a rope. You can stretch the rope, you can twist it, you can move it all around, but you can't just smooth out the knot. It's a structural feature that just persists. It's a permanent landmark in the fabric of reality. And this leads us to the paper's first really big claim. As the author puts it, invariants are precisely the observational signatures of the singular set. In other words, all of our real, lasting knowledge, the invariants, are just the signals we pick up directly from these unchangeable anchors. They are the pure signal that survives all foliation changes, which is just a technical term for saying they stay the same no matter how you slice or frame your observation. So here's the bottom line for this part. If you're looking for real, solid, durable scientific knowledge, you have to find the signals that come directly from these fundamental anchors of reality. Everything else is basically just noise. Okay, so we've got the good stuff, the pure signal that comes from singularities. But where does all the noise, the confusion, the artifacts come from? Well, that brings us to the paper's second key insight, explaining where all that scientific noise originates. The idea here is that most of reality, what the paper calls the bulk, is not a quiet place at all. It's a chaotic interferences zone. Just imagine all those different singularities we talked about, each one sending out signals. And the vast space between them, those signals overlap, they mix, and they interfere with each other, creating a jumbled mess. And this process is called the interference mechanism. It's actually pretty straightforward when you break it down. Step 1, you've got your multiple sources, the singularities. Step 2, their influences travel out through space. Step 3, those signals all mix together. And step 4, what we observe in that messy middle zone is an interference artifact. It's a combined pattern that doesn't cleanly represent any single one of its sources. And this explains why we run into artifacts so often in science. First off, singularities are like needles in a cosmic haystack. They are incredibly rare and tiny targets. Because of that, second, most of our observations happen out in the bulk, far from any single clean source, right in the middle of that interference zone. And finally, let's be honest, most of our scientific instruments aren't surgical enough to just pick out one signal. They naturally scoop up a messy mix from many sources all at once. And now, for the big payoff. Let's see how this whole framework of invariants, singularities, and interference can be used to look at one of the biggest mysteries in physics today, the problem of dark matter. So to do this, the paper rolls out a cool mathematical tool called the mu function. The best way to think of it as an interference gauge. It's a little meter that tells you about the quality of your signal. It lets you know if you're in a clean zone, where one source is dominant, or if you're in a noisy, messy zone, where tons of signals are all getting mixed together. This table lays it all out really nicely. Check out the top row. When you're in a high gradient area, say right next to a star or in the dense center of a galaxy, one single source of gravity is king. Our interference gauge, the mu function, reads close to 1. The signal is clean, almost a pure invariant. But now look at the bottom row. When you're out in a low gradient area, like the sparse outer edges of a galaxy, the pull from many different distant sources starts to interfere. The mu function's reading changes, telling you that your observation is now dominated by a messy mix of artifact signals. And this leads to a pretty stunning conclusion. According to this framework, what we've been calling the dark matter halo isn't some new kind of matter at all. It is the observational signature of an interference pattern. It's what you would expect to see when you're looking at a low-gradient, artifact-heavy region, where the gravitational influences from countless different sources are all bleeding into each other. So, wow, what does this all mean for the big picture of science? Well, this framework offers a completely new way to look at the whole enterprise, recasting it as a kind of advanced cartography. This brings us to that classic analogy, the map versus the territory. The territory is the real deal. It's underlying reality, where truth is anchored by those fundamental singularities. And the map? Well, that's everything we produce in science, our theories, our models, our data. And the most important rule for both map-making and for science is remembering that the map is not the territory. It's just our best attempt to draw it. This totally reframes the job of a scientist. It's not about finding some final, perfect theory anymore. Instead, it's about being an advanced cartographer. The job is to constantly refine the map, to discover the true landmarks, the invariants, and to get better at spotting and correcting for the distortions on our map caused by interference. The ultimate quest then becomes singularity hunting, finding and characterizing the true anchors of reality. So we're left with this one final, really provocative thought. If a mystery as huge and profound as dark matter could just be an artifact of our map making, a distortion we see because of interference, what other great mysteries of science might be exactly the same thing?